Okay, so let's do this. Let's go to Mark Sokol. You had an update on experimental work.
Yes, I have some updates, and we're also going to go to Wayne Ojala, who has been trying some new experiments, and I'm going to highlight some of his latest YouTube videos, show you, and he'll be able to comment on what he did. Most recently, I've been working on the Alzaphon experiment, which involves dynamic nuclear orientation. We're trying to create a coherent matter state using microwaves in conjunction with electromagnet. Like an NMR style electromagnet, which is pretty large. I have it over here on the other side of the shop. So one thing that I learned, I had a conversation with a waveguide expert over here in New York, who came down to the lab and checked it out. He said that we need to get a load or dummy load, which is what I attached here to the klystron. This is a circulator. So basically any energy that's coming back from our tuned waveguide will end up inside this chamber over here. It won't damage our klystron. Over here, we have two isolators, which are like one-way valves for microwaves. This is a cross-guide system, which basically tells us the forward and aft power. And finally, it ends off with a frequency isolating filter, and it's going to go into a chamber. And this is the front plate of the chamber. It's going to be about this big, and it's going to run several inches long, and we're going to tune it using the cross guides as reference. There's a connection point over here that will hook up to power meters, and we'll, as soon as we get that in resonance, we'll be sticking it inside of the electromagnet over here. And if it all works correctly, according to Frederick Alzaphon, this should make matter weightless. This is an experiment that could have been done 70 years ago with technology from back then. So this is one of the reasons why I believe in the secret space program theory, because none of this is anything new. Also, we have a cooling system that we just recently putting together. It's basically a water cooling system for the electromagnet. Water's flowing through. Here's the pump. A little radiator system, which is basically the heating core of a car. And there's a filtration system as well. We need to map the magnetic fields of the electromagnet to know if there's any peaks or any irregularities in the field, which we can then correct for. But in order to know that, we first need to map it out accurately. And you could go in there with a Gauss meter manually and map it out, but that's not a very replicatable system for mapping a magnetic field. So what we're doing is using my old 3D printer for an X and a Y axis. I attached this 3D printed material, which is made out of carbon fiber mixed with polycarbonate plastic. So it's very stiff and lightweight. And in the G code, we're going to program it to basically do an X pattern throughout the magnetic field. At the same time, we're going to be graphing the Gauss readings on a program like Excel. And then we'll be able to see if there's any peaks or troughs. If there is, we'll be fixing those using magnetic 3D printed material, which we'll print on our 3D printer. We'll be able to put in little inserts inside of the electromagnet. So we're talking about this space over here inside the electromagnet, where we'll be trying to get that perfectly laminar magnetic field. Now, Wayne, are you there? Oh, I see you. Okay, so I'm going to share screen right now, and
I made a little slideshow.
Oh, go for it then.
Presentation just to kind of talk a bit about the background concepts, because my video, I just kind of go right into the experiments, and so some of it might be kind of like Rob touched on some of it actually earlier today, so it's a little bit of, but I just wanted to share quickly. Now I have to figure out how to share my screen here. If I can't figure that out, you can go ahead.
Just let me know when. I have it ready. This is the rotating superconductors experiment that you posted on YouTube.
Yeah. Actually, you go ahead and play it. I'll see how, I'll figure out how to share my screen here, because I'm not a I'm not an expert at this.
Okay, do you see the correct screen?
I do.
Okay, I'm going to start it right now then.
So now this is a rotating device I designed to put a superconducting disk in here. It's just on a little DC motor. And I'm just going to spin it up and try different
what happens if there's any shielding effect here or disruption.
So it's sitting underneath a balance there, a cup of water on top. And there's a little laser pointer there right at the pivot point. So I'm going to show a laser dot to see if there's any deflection or with the cup of water, if it moves at all.
The RF precession, a lot like in NMR, where you excite the precessional motion of the nucleus with radio frequency at the resonant frequency, at the Larmor frequency. The rotating superconductors are supposed to set up their own magnetic field, and that's called the London moment. And because of that, it could cause polarizing field. So it'd be a lot like a type of NMR, nuclear magnetic resonance effect. So this is just a basic kind of rudimentary test. I was going to attach an accelerometer here, test for changes in just around the superconductor, changes in gravitational acceleration. And I also have this other sensor I made with piezoelectric discs in it. But for now, I'm just going to do this quick and basic one, test for any weight changes or effects on the weight of this column of water, this cup of water here. One of the things in this experiment that I have to try to rule out is, of course, air currents from this thing spinning, because it does generate air currents. So this glass plate here should shield a lot of that, hopefully. And vibration. This thing is sitting on a foam cushion here. So that will absorb a lot of vibration. And of course, I had to balance this rotor here. And the superconductor I'm going to use in this test. And I'm not making, I don't have my fingers crossed on this because it's a different kind of material. So I got on eBay. It's a titanium, barium, calcium, copper oxide, which is a different composite than the yttrium, barium, copper oxide that was used in those Dr. Pople rotating superconductor rotating experiments. And also, I played around with this in my previous video. But it's white, and I think it's like maybe a millimeter thick. I would preferably want something a lot thicker, and I would want something with the yttrium in it. But we'll see what happens. Now this is going to be kind of awkward to do, so hopefully it works out okay. Hopefully there's just enough to do this. I'm gonna move quick here.
So that little dot on the bottom there, a portion of the screen is coming from the laser pointer right in the middle of the balance.
Now, if I spin this thing up, it's going to shoot everywhere. So. Okay, here goes. I'll try to do the RPM here too. $1693, 2087, 2200, 2500, 2300, 3000 RPM, 3300,
So I'm looking for gravity shielding effects.
and laser dot, I don't see anything. 6,000 RPM, 6,500, 'Try one more time. There we go. Okay, watch the laser dot. Thousand RPM. 13, 26, 3,000 RPM. 5,000, 6,000, 6,800. 7,000, 8,000 RPM. 'Hmm. Inconclusive. Okay, so this test, I'm going to try this out, which I made some time ago. This is a super wire. I'm just going to rotate it really fast on this Dremel here. And you get to, I won't be able to measure the RPM, but it's good up to 35,000 RPM. At least that's what it's rated for, but I'm not going to go that high because of vibration. I might get maybe 5,000, 10,000. So we'll just look for any kind of movement on the laser dot there. It's going to be tricky because once I cool it, because it's going to be spinning so fast, it's going to warm up quickly. So yeah, that's going to be a defect of this experiment. Okay, so I'm going to go cool this down. There we go, it's colder. just thought I'd include this footage because it's so cool and a little dangerous. All right, that's probably good. All right. Here goes crazy. There goes. See what happened there? That's what I thought. Gonna make a lot of contact with the air. This is all frost. So this is going to be 0 degrees Celsius at the surface. And then, so most likely it's not superconducting anymore. Oh well, I tried.
Wayne, do you want to go through all of
So
these?
I'm going to do this experiment where I have in here.
Yeah, maybe we could pause and see if there's any questions, because I know the sound quality isn't very good, so it's probably hard to understand what I'm saying.
For some liquid nitrogen.
So this next part here is a different kind of experiment. It's actually with bismuth. Right, I try putting bismuth over a strong magnet in liquid nitrogen. So, but we can pause here for a minute and see if anybody has any questions, or they're not following or tracking what's going on, or.
It seemed to be a take on the Podkollev spinning disk experiment, right?
Yeah.
So,
Yeah,
so
but
if I-
also I was going to make mention of some of the things that Martin Tamar was doing years ago in his patents, and their that world patent from the Austrian Research Institute, where he talks about the rotation of a ring of niobium in a superconducting state, and they detected gravitomagnetic fields in that. And also there's some of Ning Lee's talk as well, like one of her videos where she talks about the rotation of superconductors. And so
question about your test.
Go ahead.
So when you, in your setup, you have the superconducting disk in a styrofoam cup, essentially, and you're putting liquid nitrogen on it, and then you're spinning the cup around.
Yeah.
When you, before you did your experiment, did you take a test sample of, say, a piece of standard a magnet, you know, like a permanent magnet, and place it in the on the superconductor to see what the distance was of the field, because it makes a field like a magnetic field, and it only goes so far. So to measure the field strength versus distance from the superconductor.
I wasn't looking for magnetic fields, because magnetic fields wouldn't have any effect on the experiment. What I understood from what I read about Dr. Pod's experiment from the 90s with the rotating device was that this effect, this shielding effect, extended for quite a distance above it.
Yeah,
And
well,
it
there's
was,
a near field and there's a far field. Okay, and the far field is, but you're not going to get as much signal in the far field as you are in the near field. So if you can figure out where the field dimensions are, then you can move your test sample within that distance, and you should see the effects. Follow what I'm trying to suggest is on my experiments, I'm like really damn close.
yeah. So what do you suggest then? I could hang a marble or something just above the disc? Or?
No, all I'm suggesting you do is you put the magnet levitated on top of the superconductor, and then spin it up. Okay, and see if the distance changes. The magnet weighs something, right? So you're trying to see if it changes the mass, correct?
Well, I didn't put a magnet in that experiment. There's no magnets.
No, I know, I understand, but it should work. It does. You're correct when you say it's not a magnet. It's not magnetism. Gravitomagnetism is inertial, gravitational.
Right.
So, but the magnet is, in this case, you're just treating it as a mass that's being levitated. If it'll affect the magnet, the distance of the magnet, it should affect something that's not magnetic too. If it's gravitomagnetism, you follow what I'm saying? Gravitomagnetism is not the same as magnetism.
Right.
So gravitomagnetism, you don't need a piece of metal. You don't need a magnetic object for it to affect it. It'll work with a piece of glass or styrofoam in this case.
Right. So you're saying suspend a dense material or mass just above the disc.
Right. Above the disc.
Yeah.
But first you got to figure out where the field is. And the way you do that is with a regular piece of magnet. The Meissner effect will levitate the magnet.
Yeah.
And you can weigh the magnet, okay, and say, okay, this magnet weighs this much. And then you put it, and then you spin it, and you should see that effect on the magnet. If it's gonna change that distance, it's gonna like reduce the weight or increase the weight. That should show up, correct?
But wouldn't you want to use something, I don't know, like just like a copper cylinder or something that's not magnetic? Because I don't know, I just think if I'm spinning a superconducting disk near a magnet, it might have some effect on its repulsion, its Meissner effect repulsion, or do you know what I'm saying?
I think he's saying use the magnet as a gauge to know how far you would expect the field to emanate.
You want to know, if your field's only this far, you don't want to put something over here and try and measure the effect. You want it in here. That's all. So I'm just saying the regular levitate the magnet thing, that's what most people learned about superconductors with.
Yeah.
When I learned about it, it was back in the late 80s. I worked on super yttrium, barium, copper oxide. So
yeah. Oh, I want to say just, you reminded me, any day now I'm going to be getting a YBCO disc in the mail. So I want to try that again with the YBCO because, like I said in the video, which probably no one could hear, the disc I have is not YBCO, it's something else. It's titanium, barium, copper, or something like that, calcium.
Is it still superconducting at 77?
Yeah, it superconducts. It does.
Yeah, well, that's what I'm saying is you can measure the amount of superconductivity by just levitating the magnet. It should be cool. That would be a cool experiment too. You take this other material you have, and when you get your yttrium, and see if it levitates the magnet the same amount.
Also, you mentioned, and I saw this twice in two separate takes on this experiment, that between 3,000 and 5,000 RPM, there was some change in the laser light, and that is something that Podklenoff mentioned as well. That in that RPM range, something happened. That's when the maximum effect happened, and it was when the RPM was dropping that he saw the effect. So maybe next time you want to first position that power supply in a different way so that you're not blocking the laser light every time.
Yeah,
Bring-
that was a mistake. Yeah.
So when you're slowing the RPMs, you're decelerating.
Right, during the deceleration phase. Also, you'd want to have the sample weight much closer to the spinning superconductor. Also, you'd want to have the liquid nitrogen chamber instead of going outward like a regular styrofoam cup. You'd want it sort of tapered inward so that when when it's spun up, the liquid nitrogen will have somewhere to hide and keep the cooling effect going for longer.
Something you might consider doing, which we used to do when I used LN2 for testing parts, is you take a piece of metal, like a circular piece of metal, and then you set your puck on top of that. And then the piece of metal, like a piece of aluminum would be good for this. It's something that's thermally conductive. So then your superconductor works, but it doesn't actually have to be floating in the LN2 because you have this thermal connection between the aluminum chuck, or you would call it, that's sitting on. So it spins, and then that way you can put more liquid nitrogen in your cup, and it'll keep it so it's not actually sitting in the LN2 and still be superconducting. Follow what I'm saying? It's like a thermal. Some people I've seen, they use a piece of indium metal, something really good conductor.
Okay, so put the superconducting disc on top of a plate of aluminum.
A piece of aluminum. I wouldn't say a plate. I'd say something circular, like
A circular plate, a disc. Yeah.
A circular piece of aluminum would do it too. Yeah, but it wouldn't have to be that thin as the superconductor that you're showing. You could have something a little thicker.
You could also put a plate on top of it, like a piece of foam on top of the superconductor, so to act as a thermal insulator to keep it cold.
Yeah.
So and again, with all those things that you do, each time you do it, put the magnet on it and see if it still works.
Well, theoretically, it shouldn't change. Like if the magnet is just levitating above it, it shouldn't. If you spin the superconductor, it shouldn't change.
I think what he's trying to say is use that as your gap measurement.
Exactly, your gap.
Yeah.
Your sample gap, I call it.
Right.
Okay.
The correct gap between the superconductor and the sample.
Which would mean that even the glass plate you have over here would be too thick.
Yeah. Yeah, you can't tell unless you put that magnet on there and see if it works.
Yeah.
Assuming that they're both the same effect. So this is the bismuth test, the next one, right?
Yeah.
Okay, so let's play
Yeah,
that.
it's kind of an interesting experiment.
Suddenly cause the nuclear dipole moments to reorient
I'm trying to do a type of nuclear orientation here.
and nuclear polarization. Much more pronounced than at room temperature. So I think that might cause a gravitational wave, which might disrupt the gravitational field here of this. Just a cup of water, weighing 241.32 grams. And so if there's any change here or any gravitational wave or whatever, this should cause a disruption in this reading on the digital scale. I'm also going to do a balance test after this too. And that's just cold. And I need this silly scale to stay on. 41.24. Nothing on the digital scale. 0.22. Okay.
Who knows? It might work at liquid helium temperatures.
Yeah, but you can't do that with liquid helium.
So I can't even get it here where I live, so that's out of the question.
You need a doer for liquid helium.
I don't see any disruption there.
I could get it in Vancouver, but not here.
Did you try spinning the bismuth as well?
Um,
Now for the
no, but that's a good idea.
That's something to try. Yeah.
It is.
So the bismuth isn't superconducting now, is it?
No,
Go.
scientists can't make it superconduct.
Watch that laser dot. Very being very careful not to bump anything.
I'm looking for nuclear orientation effects. So superconductivity shouldn't matter based on that.
Okay, I'm going to flip the magnet over.
Yeah, I noticed this tiny little movement there. I don't know if you guys caught that, but
Dude,
back up 5 seconds.
Wayne, apparently it only works in a Starbucks cup.
Are you saying I have to spend more on a cup?
It's a secret sauce.
Yeah, like you have to buy like a $7 coffee to get it done right.
Yeah. That's gonna break my budget.
You can buy Starbucks coffee at Dollar Tree, dude.
Rotation. Magnetic field should polarize the nuclei.
Okay, Wayne, are we going to see any actual movement here?
I did. I saw a little bit, but it's easy to miss.
Did you roll it back?
I put a little
Little mark.
finger indicator there. I don't know where it is exactly in the video.
Just looking for in-ear currents here that might cause the move.
It's weird. The first time I did this experiment, I noticed quite a bit of movement, but doing it again, I didn't see much. So it could have just been, must have been air currents.
Okay, that was it for that video. Do you have anything else, Wayne?
Well, like I said, when I get that other, when that other puck arrives, I'll revisit this stuff. Taking those suggestions to heart, and I've got this I don't know if you can see that.
It's no, it's kind of because you have your background thing on, it's kind of disappearing it.
I'll turn the background off. Oops. I can't get rid of the background. But
Okay.
anyway, it's a coil.
Not the golden gate.
The visibility, man.
I hate Zoom. Okay. Anyway, now I got to cool that down and see if I can. And it's superconducting wire, and it's based on that conical Nisicus thruster. Or that's what it is. If you all are familiar with that.
Yeah, do you run current through it for this thruster?
Yeah. Yeah, I'd run just current through it, DC current.
Maybe try like a slanted sawtooth as well.
Yeah, I try different waveforms. We'll see. I still haven't figured out how to actually set it up as an experiment, like how to mount it and stuff. I got to figure that out. Like whether to hang it on something and put it on a scale, or look for swaying like a pendulum setup.
Okay.
I don't know.
So can I see
That's
that
very-
wire again?
What's that?
I didn't see the wire, sorry. It's about 8 o'clock in the morning here, so I've disappeared a little bit. Mark, go somewhere?
Oh, I'll just quickly go through this slideshow here for what it's worth. Unless you guys want to move on to something else.
Can you share it?
Well, I did want to say something about your superconductor thing. The titanium superconductor, I looked on the internet. It's superconducting at 127K. Do you know what that means?
Liquid helium.
127 Kelvin.
No, he said 1.7 Kelvin.
Oh, I said 127 Kelvin. That's the number. So
What?
No work.
it's titanium, barium, calcium, copper oxide. Is
That's
that
60.
Yeah, it superconducts. I know it superconducts.
Well, that's not the point here. The point here is it superconducts at 127K. If you have a proper thermometer, then you don't have to go to 77K to superconduct. You just got to pour your liquid nitrogen in, give it a few minutes, and then, well, depending upon the characteristic, you have the superconductor. Some of them we have to cycle for like 30 minutes or even an hour. Depends on the characteristic. So, but at 127K, you're already superconducting. So therefore, you're using liquid nitrogen, which is already cooled to 77K. Do you understand what I'm saying?
Yeah.
So, that means very quickly it will reach superconducting capability, but you need a proper thermometer to measure Kelvin. So, or C or whatever, whatever you're used to. I mean, you Americans, oh yeah, I'm American too. Anyway, you guys tend to use Fahrenheit, which I really have no idea what it even means. So I always have to convert when I talk to my brother and my mom.
Celsius is a lot easier. I agree.
So find something that you're comfortable with, measuring the coolness, and then you'll know right away when it superconducts. Now, what it means, the what did I say? 127K. This is called a transition temperature, and transition temperature is what defines when a material becomes superconducting. Now, YBCO will be, depending on the material, will be superconducting between 80K and 95K. So mostly ours 5, but some companies, because of the way they process it, it's 8, it can go down as low as 80K. But you really need a thermometer so that you know when you hit the transition temperature. Because before that temperature, you're not superconducting. And one thing I can tell you about YBCO is that it takes time to get to 94K. And if or whatever temperature that we're running it at. So, but anything below 100 takes a lot of time. And you had to pour copious amounts of nitrogen in order to get to that temperature. Also, you need a double-walled container so that you don't bleed out the heat and your nitrogen just doesn't boil away. So you have to be more careful the cooler you go. And it takes longer the cooler you go. And to reach 77K, which we've done, but that requires a lot of insulation and a lot of time, up to an hour in some cases, to reach that temperature. So yeah, so anyway, get yourself a good thermometer that you feel comfortable with as far as the temperature is concerned. And then the rest of it is pretty much what I described. Okay. I work with superconductors every day, so I know a lot about this.
So I got this link that I'm putting in the chat right now that is to this company called Lakeshore that makes cryo thermometers. Like,
Yeah, you just had to pick the most expensive company on the planet.
well,
my-
it gives them an idea of what they need. They can probably find a knockoff.
Lakeshore probes are $5,000 a piece. That's just the temperature probe.
Yeah. Okay.
The Lakeshore equipment is over $10,000 to $20,000. I'm pretty sure that he doesn't have that kind of money.
Okay. What do you suggest?
But you don't need that kind of money.
No. What brand do you?
Can I'm not. Okay. Yeah, that's good. I'm not really understanding why it's necessary to be able to measure the temperature, though.
Because if you don't know that you're actually at the critical temperature, you'll never know if you're really superconducting or not.
I know it was superconducting because it could levitate little barrel magnets.
Yeah. Okay. That works.
No,
Yeah, it's a lot cheaper than buying a temperature probe. Also, you have to consider how do you attach a temperature probe to a superconducting magnet.
Especially when you're spinning.
Yeah, especially when you're spinning. There goes your Lakeshore $5,000 probe. Yeah, this is all superfluous. If there's liquid nitrogen on it, it's cold enough.
Yeah, I apologize for
It's
that. That's what
be.
I used when I worked for Hughes, and they had lots of money, I guess.
well, there are ways that we actually do spin our stuff sometimes, and there are ways to do that. There are techniques to deal with that. So you don't actually have to be on the superconductor. You just have to be in the general area. So unless of course you're doing the JC temperature, then you're not spinning anything. You're actually attached to the superconductor itself. So, but you of course are not doing JC temperatures. Yeah, look, you can do whatever technique you want to do. But if you want real data, you're going to have to get a proper probe.
Well, I think, but I think as in terms of rough data, Will, I think if it's levitating barrel magnets, right, then we can assume that it's superconducting. So yeah, I think I understand what you're saying. There's, it's horseshoes and hand grenades, right? It's like, how precise does it need to be? So for, but the laser experiment was interesting. I did see that laser jump too. I think it would be interesting. One of the things I'd wondered about, and I could be way off base here, but so Wayne, it looked like the laser was coming straight down, right?
Coming straight down?
Yeah, it looked like it was kind of coming straight down next to the superconductor with that one. That was the one that I thought was interesting. Is there a way that you could bounce that laser off? If you bounced it off the superconductor, I don't know. The reason I ask is if you had a bounce, that deflection angle should amplify any changes, right?
Right.
So it might be more, I don't know. It might be worth trying.
Yeah, no, that's a good point.
Yeah. I see what Will is saying though, but he's used to working because he works in a lab, so he works very precisely,
Right. Yeah, right now I'm just looking for a pass or fail, really. Just like, does something happen? Does anything move? As far as getting data collection and stuff like that. I was trying to go down that road with some accelerometers and hooking them up to my laptop and getting like real-time data acquisition and all that, but it's I haven't figured out all the technicalities of it yet. So I just wanted to see, if there's anything visible. Can I see anything happen at all?
Well, and then there was the water. Remember, and this was the pulse generator experiment. I think that Mark and Jeremiah did, but they, but then we were talking about bouncing the laser off the water also. But that might be, I don't know, maybe it wouldn't matter because it's not a pulse. It'd be interesting to see if you put this thing near water, if it would have any effect.
Yeah. Yeah, and it's always like eliminating vibration is a big deal. I'm finding vibration is everywhere and air currents and stuff. So
I think it's a neat experiment though.
Those are always the
and I love watching the videos. It's it's cool to see. And I think also stuff like this is you're helping to educate people about like how to do stuff in the garage. That's the thing. Well, I know that seems weird, but a lot of people are like, they don't know how to. They're like, how do I do this without spending $1 million or?
Yeah. Well, a lot of us are hung up on excuses, so it's like a lot of it is just ego, really. Like I don't want to look bad. Like doing something with broken electronics, or if I can't have a $25,000 piece of laboratory equipment, I'm not going to even try it. And
Well,
that has its merits. Sure. I mean, you got to be able to get quality data and stuff, and you need quality equipment to get quality data. Sure.
Well, I want to point out a couple of things. Number one, actually, when we started out, my company started out before we got invited to my alma mater, my university. So we started out in a garage, and then we ended up in the university, and now I run 2 multi-million-dollar labs. But that took 8 years to develop. That's not something that happened yesterday,
Mhm.
So, and I still build stuff. Right now, actually, I'm building a laser microscope because I don't want to pay $25,000 for a laser microscope. So I can just build one. So just because I have a lab that has very impressive amounts of money, which, like I said, was over 8-year period. doesn't mean that we waste money by buying $100,000 microscope. So I want to point out something about superconductivity. You don't need a $20,000 piece of equipment like what we have, and literally we do, to do that type of stuff. When we were starting out with the superconductors, we used I think about $350 instrument to basically get the temperature, because we needed the TC to see what was going on. So you can start cheap, and eventually over time you will build up to a much better situation, but it takes time.
Mhm.
Steve Jobs didn't start Apple, in the ivory tower. He started in the garage. I think everybody does. So,
Go to Larry Page.
It was Wozniak's garage, wasn't it?
Larry Page started in the garage.
yeah, well, see, I rest my case. So, yeah, so anytime you want to know low cost ways to do things, let me know. But one thing about circuits, be very careful and isolate them from the cold, because circuits change over temperature, and they have a temperature range, which the instruction manual will tell you exactly what that is. But be very careful about isolating them from hot and cold, because you don't want it. Once you go above their or below their operational temperature, then your circuit changes in the characteristics, and then you have total junk data. So keep that in mind, especially on those accelerometers. It's a good idea, by the way, but just be careful.
It changes the resistance. Hey, is it Dr. Reichen?
Regan, actually.
Reichen? Okay. What would it be within your capability to try this in your lab?
Yeah, if I had the time. I don't. So please carry on. So
Okay.
I've had several people on this channel ask me to do experiments. Some of them even offer to pay, and I don't have enough time. So I got my own stuff that I'm doing, and I have schedules for that. So.
Okay.
I got a question for you. Which Nazikas thruster design are you going off of? I think there's 3 different versions of the thruster. So which one are you modeling your experiment off of?
The coil. I have a picture of it somewhere. I don't know if I can find it in a timely way though.
Because I think like the 3rd version didn't work.
Well, I saw this little video from Paul LaViolette, probably, I don't know, 6 years ago or something, and they were trying to raise money to get a superconducting coil made, but it had a slight taper to it. And so that's basically what it is. It's just a slightly well, it's a cone-shaped coil. It's tapered, and so apparently it's supposed to work.
I found.
It's supposed to work
Oh, I
by.
didn't mean to interrupt you. Go ahead.
Oh, I'm saying it's supposed to work by the Meissner effect or something, where like superconducting coils, when you power them up, they have like an internal pressure that tends to drive the walls of the cylinder outward. And so if you taper the wall.
Yeah, I'm new to all this, but like,
yeah,
I think Paul did post an update on his website relatively recently about like, it was a Nazikas thruster that him and Dr. Nazikas did test, and they had a GoFundMe. I don't know if this is the same one, but the one they did test, they said they didn't get a result for. but they never did test the original design, like version 1, whatever that was. So,
Well, I've seen the video of the one with the permanent magnet and the tapered superconductor, and that thing suspended on a long string or something, and it was moving around a bit. But yeah, so I don't know which one you're referring to. I haven't looked, but I just got this wire, so I thought I'd give it a try, see what happens with it.
that's awesome.
Yeah, I look forward to it.
I actually just ordered some bar magnets for that spinning disc experiment with the poles in the center and on the outside all the same. And I'm actually gonna have to reorient the poles on the magnets when I receive them. I should be here tomorrow, so I'll be able to run that experiment over the weekend.
Sounds good.
Yeah, the wonders of living in the United States, next day shipping. Wayne, when's that package gonna get to you?
Good question. It's made it across the border, so that's the major hurdle. Should be here any day. Probably, I wouldn't be surprised if it shows up on Monday.
There's I put a silver coin in there too.
Silver coin?
Yeah, well, it's a good it's the best conductor of electricity at room temperature without going to superconductor. So you'll see what you can do with it.
Yeah. Throw it in some liquid nitrogen and something like that.
Everything needs to go in the liquid nitrogen.
Baptized in the nitrogen.
It gets baptized in the nitrogen.
The purification.
I see Jeremy's getting a kick out of something. Jeremy, what's up? How's our YouTube following?
It's going, dude, that panel was sick, man. We had over 200 people watching. It's dropped by about 70 or 80 people right now. And, but we got some lively characters in the chat arguing with me about Corbell and saying that his comment was that I ask for money way more often than Jeremy Corbell. Like when does Lazar or Corbell ever ask for money? I was like, they don't need to. They charge for their documentary. And my response was, yeah, I sold out to the military, man. Asking for donations for free, truthful, factual, well-researched content is so much worse than charging people for lies.
Yeah, and even if you get it for free on Netflix, you're paying your Netflix subscription. That's how they get paid for the Lazar documentary. He didn't make that for free.
Oh, I'm sorry, man. I was laughing at that one. That was great. Yeah, okay. I asked because I have to, man, because this is all user funded, man. Anyone, I ride on my donations for the less than $100 I've made in super chats on this live stream so far, man. Yeah.
Jeremy, how's your research into material science going?
I mean, I read stuff every morning. I get new stuff sent my way, but it's really, I rely on this community, man, more than anything. I get so many experts that I come in here and know so much more than I could ever learn at such a younger age that I'm just like, you know, we're getting newer people coming into this field, newer people coming into this when they realize, you know, the potential of this technology. And I can't touch what these people can do. And I rely on this community and you know, this. And honestly, I've been working my other construction job and doing this on the side. So like, I haven't had as much time to do like nonstop constant research, but it's just great. The amount of people that I'm meeting and talking to and getting a hold of, but metamaterials are definitely key. And, you know, I was interested in some of the points that were made earlier about the market and the infrastructure for the industrial infrastructure for making this, you know, and it resonated with me with a couple other comments I've heard in some of these other documentaries. There was this Russian USO doc And some of their intelligence people, they did an analysis to see if this could have been, you know, foreign technology. And with what they determined was like, it would be as if all the resources in the entire world were working full time just for the sake of producing these craft. There's just no way that we could, you know, we could produce this, and there's not enough money in the whole world to do it. And, you know, or maybe there is, maybe we there's more about these banking systems than we really even understand, and where all the money does go. But it's just, it gets into this, all these esoteric arguments that go back to like the dawn of time. And I love it, man. It's opening up all these new conversations, because a lot of people, this is like the mass awakening. It's really great. More and more people are really researching and diving into the information, and really getting beyond what has just barely broken on the surface in the mainstream media. So,
As a material scientist, come on here to talk to you guys about like metamaterials and all that.